Good afternoon to everybody. Let me start thanking Michael and Getty Conservation Institute for inviting me for presenting the results of our most recent research work. However, what I would like to share with you during this presentation is much more the philosophy that there is behind our research work, and that is summarized in the title of the presentation that could seem a little bit cryptic at the first reading. The actual meaning is that I'm very deep convinced that a wooden panel paint is, or at least behaves, like a complex system. And this morning we start discussion about terminology. I would like to bring my contribution. I think it's important to make a clarification about the differences between complicated and complex. When we are going to analyze a system, complicate means that we are able to give a complete description of the system and the interaction that there are between the components of the system. Complex means that the components that make the structure of the system are able to interact each other during the time and with the environment. And this is a big difference. And it has also an implication for how our modeling works. Because if the system is, let me say, complicated, in such a system we can study in a separated manner the component of the system. We can adding the different component of the system for trying to deriving the behavior of the system. And we can make forecasting of the behavior of the system during the time. It works very often in what we call a linear behavior. In the case of a complex system, no one of these possibilities it is allowed, because there is an interaction between the component of the system. What is complexity? If you look for a univocal definition of complexity, probably you can't find it. I have not been able to find just one definition of what complexity is. Very often, complex systems are described through the behavior that they have. And you see here a list produced by Paul Cilliers, that is a very important research in study of complexity, that made a long list of what are the typical behavior of complex systems. That, in few words, means that these systems are made of components that interact each other, as we said, and they interact are open systems that interact with the environment during the time. I'm sure that if I shift to a panel paint and its behavior, you can easily agree that most part of this behavior are typical also of panel paintings. But in my opinion, the crucial point is complexity shifts the problem from the analysis of each component to the analysis of the relationships. This is the big issue. In complexity, we have to carry the interaction. And that makes the difference. And to make much more intricate the questions, there is the presence of wood. And the structure of the material is the results of an emergent behavior of a true complex system, that is a biological complex system, that is the tree. And in building the structure of the material, you have the effect of randomnesses in every scale, in every scale, at every scale in the structure of the material, starting from the micro structure with the disposition of microfibril in the density of the material in the presence of the defect. And even in the aging of the wood, complexity proceeds, because doesn't matter what is the biological damage that is very easily to be assessed, but during the time, the wood undergoes a modification system that mostly due to depolymerization, auto-depolymerization of hemicellulose. By the way, it produces a lot of bad gas that you can find. We measure the effect of this process in terms of emission of volatile compounds that are very, very dangerous. But the point is that this process, in a time frame of centuries, can produce measurable effect in the outermost part of the elements. And these changements are very important because they affect both the equilibrium moisture content of the wood and the stiffness of the material. That are two parameters that are very important for us. So we have a very, let me say, simple structure, because if we look at the structure of a panel painting, we have very few elements. That is, of course, the wood and the anatomy of the wood, the presence of the ground and the color, and glues, of course, we saw yesterday, and sometimes canvas. Very few variables. But like in a checker game, when you have few rules, you can play an enormous amount of games. It is exactly the same. And, as we said, this system is able to interact with the environment during the time. The results of that is that this system acquires evolutional behavior. Evolutional behavior that under the control of the causality, as any evolution behavior in nature. So what we have to know for modeling the behavior of a single panel paint, that was our aim. We have to know the material laws, we have to know the boundary condition, we have to establish the boundary condition, and let me say, it is very important, we have to know the state of the system at the given time. And here start our works that has been carried out in cooperation with Opificio delle Pietre Dure in Florence, and that it has been the object of a PhD project of Lorenzo Riparbelli that made most part of the work that I'm going to present now. What we did? We selected what was, in our opinion, considering even previous work that we have done, what are the most important variables that can affect panel deformation during moisture variation. And of course, they have the exchange behavior of the two surfaces, of the painted layer and of the back, the stiffness of the paint layers and of the wood, the diffusions, and the stiffness of the crossbeam. Using these parameters, we using a finite element model that is a rule-based model, what we got is a result like that. Here you can see what is the response of the model considering the different anatomical structure of the board and the different level of rigidity in the point layer and the emissivity of the point layer. You see here you have a family of behaviors that are possible. And look at how change the behavior of a point when the emissivity of the point layer is very low. That means that it is possible to have very strong different gradients between the two phases, and the so-called flying wood behavior, it is allowed. The same type of board, if you increase the rigidity of the ground layer, doesn't allow anymore this behavior. That is what the model tell us. So we said, okay, look at what's happened on real. Sorry for using real. I know that it's not politically correct. True ancient panels. I hope that, but let me use real in the proceed. It's very interesting because monitoring the actual behavior, what we have seen. We have seen that really the emissivity of the point layer and the rigidity are able to define the behavior of the panel during moisture transition. This is very interesting, but it's much more interesting if you compare what's happened here. This is the actual behavior of the point with the gray curves here. These curves refer to the same panel when we cover with a moisture proof, a moisture barrier, the behavior of the point surfaces. As you can see, the behavior of the point change, exactly how our model forecast. You see, it is the same behavior, it is the same panel, changing the permeability of the point surfaces. It changed completely the behavior of the point. So we can start to feel the list. We have seen what are the property of the panel, but what is more interesting? This is the same reproduction of the picture that we saw before. It is relevant to just one panel. This is the possible combination, the possible state. It is what we have called the domain of existence of a panel paintings. In my view, it is a three-dimensional space that these variables are able to establish. And within these three-dimensional spaces, any actual points can find its own way according to what was the original structure and to what has been the evolutional behavior during the time. That is due to the interaction with the environment during the time. And we have seen that the effect of that is that this behavior can change. And it is why I said it is very important in order to forecast the behavior of this specific pint, to have the possibility to establish the state of the system at a given time. And it is what we did, applying a methodological procedures that we have established during the time. We can establish making loading tests. We can establish the stiffness of the wood and of the system. Using these devices that we call the deformometric kit, we are able to measure in real time the cupping variation of the pint during moisture cycles that we have applied to this structure with crossbeam and without crossbeam, repeating the cycle 2 times. 1 times normal condition, and in the other case, covering the surfaces of the wood in order to have a real barrier to the moisture content. Through this system, as you can see here, we can measure what is the diffusion time of the moisture inside the pint layer. Okay, and we did this experience on 6 different pints that were chosen according to what has been the typologies, the evolution of the typologies of the Italian school. That means poplar wood with different thickness in the ground layer. That was larger in the older one and thinner in the more recent one. And through a process of optimization, we were able to establish the actual values for the parameters that we have included in the model. And the results is very, very interesting because you see here in gray there is the modeling, in orange there is the experimental data. The model resists to the experimental data. It behaves like the original pint. It is very interesting, this number here, because it is important for us. You see, the R square means how much part of the variability is covered by this system of variables. Here it is quite high. The lowest value that we have got has been 0.92. That is a good news because it means that this parameter seems to be enough for describing the behavior of the pint. But please consider a very important issue. It works, but is a time picture of the behavior of this pint in this moment. We don't know what could be happening to this structure in the future. What could be the evolutionary behavior of this structure? It is a complex system. Very interesting, very briefly, was the results of the analysis, sensitivity analysis, that show us both in local analysis where the effect of each variable is separated by the other one, and you see that each one is able to have its own behavior And it means that each one of these variables interact in determining the behavior of the painting, and the so-called global analysis, where we consider the effect of all the variables at the same time. This is the Sobol. We use the Sobol test that is made even for selecting the importances of the variable in a process. What is interesting here, what is telling us this analysis, that we repeated at 3 different steps of time, after 3 days, 6 days, and 9 days, you see that the importances of each variable change. That means that the system change. And Sobol teaches us that higher is the differences between the single analysis with the total analysis, higher is the interaction between the variables. So we have interaction within the variables. That is one of the characteristics of our system. The next step has been having a model that behaves like the paint, the actual paint, to make a digital twin. A digital model that behaves like the original one. And what has been the use that we have done of this digital twin? First of all, we were interested in understanding the function and the effect of the crossbeam. That was one of the questions that came from the Opificio. You know, they use a particular type of crossbeam that is made with springs. And the question was, what is the loading that we have to give to the crossbeam? So it was one of the main questions. And the digital twins can give answer in this way. And you see, it is able to make a simulation of what's happened inside the paint. Here, the paint is represented by each of these gray columns. The darker gray is the paint layer, and this is each column represents 1 day. So it's the evolution of the transition of each paint with crossbeam and without crossbeam. And you see there are some behavior. At the beginning, the stresses is concentrated in the back, and during the transition, the stress move and affect heavily the ground and the color. And this is another point. You see more or less the behavior are the same. The values are completely different, of course. In term of stresses, you see the number, probably I don't know if you can read, but the numbers are completely different. And so there is what the model, the digital twin, teach us is that probably there is a differences in the transit, in the short period at the beginning of the transition, where the larger stresses are in the back, and little by little, as the system reach the new equilibrium, there is a transfer of the stresses to the painted layers. Yeah? And so it means that the function that the crossbeam play is that of reducing the strain of the system. It increases the stress that in most cases seems to be affecting the painted layers. But much more interesting for me is a window to the future. Because if it is true that this system is able to simulate the behavior of the real object, we have one problem open. That is the variation of this system during the time. We said that we take a picture of today, but what's happened in the time? A possible help came with the help of EOT technology in establishing a permanent flux of data and information from the object to the digital copy. That means that we are moving in the so-called metaverse. The metaverse means that is a new environment where we can simulate the behavior. And the implication even for conservation, in my opinion, are very, very promising. I'm going to finish. Because you can use the digital twin for predicting the behavior, at least, of course, in a short time. And then it can be used for the management of the pint and possibly even of collections. We are a step away from using the pint for controlling the environment around it. So the time is finished. Very, very briefly, let me resume what I think is to be the most important aspect. I hope to have been able to explain why I strongly believe that a panel painting is a complex system. And there are 2 or 3 implications that are very important, in my opinion, for us. Because if it is true that it's a complex system, what we are not allowed to do is to use, this morning we talk about the use of samples, copies, monks. Okay, it is important, it is interesting, it is the way that we have for learning something. But to move these results to the real object is another matter. Because sometimes they represent themselves. And we have each cases that is quite different from another one. The same is for collection. And even for restoration. Many times restorers study previous solution. That is a good habit. But be careful, because this solution, even if it has worked properly, it has worked properly in a different system. This, unfortunately, is a limit. Complexity brings us in front of the limit. And I think, I'm afraid, that we have accepted. Thank you so much for your kind attention.
Yeah, thank you very much. We have time for questions. So I'll ask one. So one of your points was that each component responds to its local environment in a well-defined way. So that's a non-complex part of it all, I guess, right? Each component responds to its local environment. So that can be studied independently of the whole system, I guess, right? What that response actually looks like. Yeah.
Here you see the effect of each single variable in the behavior of the system. The local analysis make a separation of the contribution of each one of the parameters that we have considered to the behavior of the system. It is isolated by all the other one. So each one of these lines represents the behavior of the variable even if it was the only one that
Okay.
could affect the system.
Okay.
Marco, I've got a question. So I understand from your talk that this selection of those parameters is non-reducible. So this is this minimal amount of the variables you need in the model to reconstruct behavior of the painting. But my question is like, how you look at the extreme boundaries for those parameters? So do you have the like well-defined minimum and maximum limits for those parameters to play with?
We started at the beginning substantially these picture here came using the values that came from our previous research work for the characterization of the wood mostly, and what we have found in literature about the rigidity of the paint layer. That was the way in which we setting these two intervals, okay? That was the beginning. During the process of optimization, we derive the value of the parameter from the real object, okay? Starting from that values. And we make, through an optimization process, the definition of the specific parameter of this work of art. It is why we made characterization. It is what we call learning from object approach.
I think Lukasz has the mic up there.
I have a question regarding the parameters. I couldn't see very well. So what was the elasticity modulus of the paint layer you determined, and what was the uncertainty of this determination? Because I understand that in your inverse method, you determine the stiffness, for example, of the elasticity modulus of the paint layer. Am I right? And what are the values? Can you tell us?
We start from, let me say, approximately 0 to 10,000 megapascal. That was the field of variation. Concerning the values that we determining during the characterization process, here you can find the value of the single. Oh, its range in this case is 1,506. That was for this specific. In other case was around. I'm going into memory. It was around 2,500.
So 2 gigapascals.
Yeah, yeah, megapascal.
Yeah. Yeah, 2,000 megapascals, 2 gigapascal, right? Okay, let's thank Marco again. So.